This is a survey paper on cryptographic hash function algorithms and message authentication by Apala Shakuri, Temitope Dele, and Radhika Chakrabarti. The focus of this paper is on cryptographic hash function algorithms and message authentication. Basic information about this topic is reviewed, and then methodology of some algorithms are explained. After that comparison, theories like MD4, MD5, MAC, and their applications will be reviewed. Hash functions were introduced in cryptography in the late 70s as a tool to protect the authenticity of information. A cryptographic hash function is a procedure that takes data or a block of data and returns a fixed size bit string. The data to be encoded is often called the message and is sometimes called the message digest, which is where MD that we had in the previous slide comes from, MD4, MD5. Now we're going to be talking about cryptographic hash functions. The cryptographic hash function is divided into two. We have the MAC, which stands for Message Authentication Code, and then the other part, we have the Manipulation Detection Code. And the manipulation detection code, MDC, is divided into two. It's further divided into two. We have the OWHF, which stands for one-way hash function, and the CRHF, which is the collision resistance hash function. This will be discussed in detail in further slides. First, we're going to be talking about the one-way hash function, the OWHF. In the hash function, in this one-way hash function, Y is in the image of H. The hash function must be one-way in the sense that Y must be in the image of H, and it has a message such that H of X is equal to Y, and H of X is hard to find in a message. Then we have the collision resistance hash function, which is the CRHF, and in this function, or here it says that the collision resistance hash function is a function H satisfying the conditions that the argument of X can be of arbitrary length, and the result H of X has a fixed length of n bits, and the hash function must be one way in the sense that a given Y in the image of H is hard to find a message such that H of X is equal to Y. And the collision resistance hash function must be collision resistant. That means it is hard to find two distinct messages that hash to the same result. And then we have the MAC code, which is the message authentication code. It's pretty much like the one-way hash function with this just the only difference between both of them is the MAC is more common. It's more commonly used today than the OWHF.
Coming to the complexity of generic attacks on different properties of hash functions. Here, the complexity is very important compared to the security, and the one-wayness of the algorithms have the complexity of 2 to the power of n-1, and the second pre-image resistance have 2 to the power of n-1, and the collision resistance is like the MAC. Simply it contains both the one-wayness and the second pre-image resistance. And coming to the message digest function, the message digest function creates a unique digest for each unique document, and the message digests are also called one-way hashing functions because they produce some values that are difficult to invert and widely efficiently unique. Many messages that consist of digest functions are like MD4, MD5, MD2, and secure hash algorithms. Coming to our new approach, the hash function of the MAC mechanism should be easily replaced with other hash functions if necessary. And the NMAC-A approach has two cases. Like the first case will have the NMAC-A MD5 message authentication code algorithm, which takes 128-bit key as an input that produces 128-bit MAC. And this is a more conservative approach to build a MAC from MDC. The MDC MAC is such a technique that it takes 4 32-bit initial value of MD5 by the secret key K. Coming to the algorithm, the input takes 128-bit K such that the output has to be 128-bit hash code of X. In the first step, we have to define 4-bit initial chaining values, which consists of 4 hash functions H1, H2, H3 and H4, and we go with the 4 auxiliary functions which contains 3-bit variables, each consists of 32-bit, and the operations among the 3 functions with variables is like AND, OR, NOT. So we define an additive 32-bit constants in order to provide the radians and the bit value and the absolute value. And coming to the security key, we define a key with every permutation table of from positions from every 16 bits, like 0 to 15, 16 to 31 and 32 to 47 and 48 to 63. From 0 to 63 we define key for every 16 bit, and then we define the number of bit positions for left shifts for using the security key K. And coming to the pre-processing, we use a padding in order to append a single bit that gives the radians of 512 minus b plus 64 mod 512, because we used to have 512 bit block number resulting the string as shown. The formatted input consists of 16 M32-bit words, which consists of x0, x1, so on 16 M minus 1. And coming to the process, this process consists of 4 rounds, where each round of 32-bit word is kept into a temporary storage. Then process these hash functions into a 4-round hashing so that we can get each pre-image of a normal hash value to the hash function, and finally the MAC is concatenated with all the 4 hash functions such that we get a MAC and a encrypted output of 128-bit.
Experimental results. A number of experiments are performed to compare the performance of various hashing functions like MD4, MD5, MAC MD5 and NMAC MD5 in terms of speed and avalanche effect. The high avalanche effect of NMAC MD5 is basically due to the high randomness it possesses. Applications of NMAC MD5. The message can be a string of any variable length containing both lower and uppercase alphabets, digits, and special characters. The message digest is again a string of fixed length containing all the alphabets and special symbols. This security is used in MySQL databases and PHP for web applications. Scope for future development. There exist numerous scopes for future development. Firstly, the present algorithm for calculating the message digest is susceptible to brute force attacks. This can be improved to prevent decryption by any ordinary means. Secondly, there is always a scope of improvement for the space and time complexity of this algorithm. Thirdly, we see that NMAC MD5 shows a random efficiency of around 70%. This can also be improved in future works. This paper clearly shows the improvement of NMAC MD5 over all other algorithms, which is demonstrated through the graphs herein. Based on experimental results, we found that this algorithm is as fast and robust as MD5. Thank you. Our presentation is now open for queries.